Welcome back to Algebra 2. In today's video, we will take a look at transformations of functions. By transformations, we mean translations, reflections, and stretches or squeezes in the graph of a function. In Algebra 1, you learned about the slope, intercept, and graph of a linear equation. You also learned about the vertex and orientation of quadratic equations, meaning parabolas. Today, we will look at how small changes in the formula for a line or for a parabola affect the graph. We will extend this to functions we started using this year, including radical equations, exponential equations, and logarithmic equations. In this CAMI, you will be graphing a lot. It is hard to graph by hand in the accompanying worksheet, so a sketch is adequate, but you should plot some real points, especially x or y intercepts, vertices, and also asymptotes or any other helpful feature, and then draw the line or curve as best you can that passes through the points you know or approaches the asymptotes you know. Let's get started. The first thing we will examine is the effect of adding a constant b to a function. That's what I have here. So I have base functions, linear, quadratic, radical, exponential, and logarithmic. And the base function means the simplest possible version. So of course, the simplest possible linear equation is y equals x. But so now I have y equals mx plus b, or quadratic would just be x squared. Here I have x squared plus b, etc. Okay. So here are 5 functions with the b added to the equation. By base functions, I mean the simplest possible linear, quadratic, or other type of equation. Notice that in the case of the linear equation, y equals mx plus b, b is just the y-intercept. So we know if we change it but don't change the slope, the line moves. Does it move horizontally or vertically? Either vertically. Let's take a look. So I've got a linear equation here with a slope of 2, and b is my y-intercept, and you can see right now b is set at 0. And then I have y equals 2x plus 3. And if I move this b around, you can see that it shifts the red one up and down. Is that going to the left and to the right, or is it going up and down? Clearly the y-intercept is going up and down, but the x-intercept is going to the left and right. So what do we call it? I'll leave it for you to answer that question. Think about that. Okay. In this exercise, I'm going to keep b at 3 for my graphs. All right, so I'm going to pull this out and put in a graph here for the first one. And you can see I took this one. Oops. Get rid of that. Bring this little guy here and paste it on top of this one. Let's drag that there. So there's the y equals mx plus b, and the red one is when b is 0, and the black one is when b is 3. Let's do the next one. Quadratic equation. What does moving the b do to that? Let's have a look. So here I can see that b is 0 right now, and if I start sliding this around, let me see, why did it not give me a, there, I want a slider. If I start moving the b around, you can see it moves like that. Okay. Is that a horizontal or a vertical change? All right. Let's push that one away and bring out the quadratic one. And I'll paste it here. All right, once again, the red one is y equals x squared. The blue one is y equals x squared plus 3. All right. Let's take a look at the next one, which is a radical equation. What does adding b to that one do? So here you can see I have the base function, y is the square root of x. Then I have y is the square root of x plus b. Let's slide b around. Okay. See what it's doing. The endpoint's always on the y-axis. I'm going to leave b at 3. And you can see here that this point on the end is 0, 3, just whereas this one is 0, 0. Okay, let's cut and paste that into my document. All right, next is the exponential equation, f of x equals 2x plus b. Let's try that one. So here I have y is 2 to the x, and I have y is 2x to the x plus b. Let's slide b around and see what happens. Oh, isn't that interesting? My hockey stick is going up, going down. I'm going to set b in 3, like I did on with the others. We get that. Okay, I'm going to paste that in. Bring my hockey stick over. Paste it in. That one doesn't fit very well. I'm going to squeeze it down a bit. Okay. And last but not least is the logarithmic equation. All right, I know we haven't graphed logarithmic equations very much. Let's try that one. Bring that over. So here is a logarithmic equation. Notice that it's very similar to the radical equation, except this one is asymptotic. This blue line goes down, down, down. You look at the square root, that stopped right there at the origin. That stopped right there at 0, 3. This one does not stop. It keeps going down. So what does b do to it? Well, you can see I've got the base function, log base 2 of x, and then log base 2 of x plus b. And when I slide b around, it does that. Okay. Is that a horizontal or a vertical shift? That's the question. All right. Let's bring that over here and paste in my picture of the logarithmic equation. Oops, I went to the wrong page. This page here, and paste it there. So there's my logarithmic equation. Make it a little bit bigger. So looking at all of these, what do you see? Is that a vertical change? Did AM change horizontally? You know, you could argue that the first one went both or either vertically or horizontally, but the rest clearly, the vertex was in the middle, vertex is still in the middle. The end was on the y-axis, the end's still on the y-axis. So it's not shifting to the left or right. This one, it's really kind of hard to tell, but you can, one thing you can see is that the asymptote here in the red is on the x-axis and here it's up. So it's like we pushed up the asymptote. And here we can see that we have raised this purple from the red. Okay, so changes in B, let's answer these questions. Cause a vertical translation. All right, so let me just put this here. Changes to 16, and I can put in here a vertical translation. Right? And it either lifts up or pushes the function down. So I'm just going to write that with my pen, my trusty pen here, if I can. It lifts up. Oops. It lifts up. No, I'm not on a pen. Try that again. All right, it lifts up or pushes down. Or pushes the function down. Okay, vertical shift. On the next slide, we'll examine the effect of replacing something else. So again, to summarize what we did on this slide, we added b to each function, and we saw that it was effecting a vertical shift. All right, let's go on to the next slide. Here, I'm going to replace in the function x with x plus a. What does that do? Let's have a look. So the first one is the quadratic. All right, I'll put that in here. And we have the base function, y equals x squared. And then notice what I did here. I replaced x with x plus a in parentheses, because I want to make sure I replace the x, not just square part of that thing. I want to square it all. Okay? And notice that right now, there's a red graph shown, and there's also a blue graph shown, but that's because a is 0, so those two are equivalent. When I slide this around, oh, look what happens. Okay? So when I change a, the graph appears to move left or right. How do I make it move right? I move the blue slider ball left. Does this always work? When I push it to the left, it moves to the right. When I push to the right, it moves to the left. Let's find out. So that's the quadratic. Okay, I'm going to bring that in. And once again, I left a at 3 for the purposes of this graph that I'm pasting here. Oops, that's not the right one. Go back and get this one. Oh, it's because it's not on. There we go. Yikes. There we go. All right, put this here and bring this one down and paste that there. So there's the quadratic with a has gone to 3, and that's the blue one. Notice that the vertex is now on -3. All right, let's try the next one, square root. Okay, bring this little guy over. And again, I replace the base function with x plus a. I have my slider. What's it going to do? When I move to the right, watch what happens. Oh, it goes left. When I go back to 0 and then start moving to the left, oh, it goes to the right. Okay, and I'm going to leave it on 3 like all the others. Okay, and I will paste in my picture, which looks like this. All right, so again, this one I put in a is 3, so the red is the original, and the blue is the square root of x plus 3. All right. How about exponentials? Let's look at that next. Exponential. Bring this little guy over. Okay. Here is my base exponential, 2 to the x. Then I change it to 2 to the x plus a. I have my slider. What's going to happen when I move the slider to the right? Oh, it goes left. What about when I move it left? Oh, it goes right. Let's leave it on 3. Oops, too far. Right there. Okay, so the red one is 2 to the x. The blue one is 2 to the x plus 3. All right, let's grab my little image here. And we have, paste that in. All right, and the last one is log base 2 of x plus a. Let's bring over log base 2. Where are you, log base 2? Come on. All right, log base 2. Here's the base function, log of x, log base 2 of x, and then log base 2 of x plus a. Let's slide it. When I slide to the right, what's going to happen? Oh, yes, it goes to the left. When I slide to the left, oh, yes, it goes to the right. Okay. I'm going to leave it on 3. And there it is. Okay. And I'll cut and paste that into my picture. So we have this one. And I'll paste it in here. Now notice that the blues are always on the left. And I made A +3. So let's answer the question. Changes in A cause a horizontal, right? This time, it's horizontal change. I'm just going to write that with my pen. Horizontal. Translation. When A is positive, I'm going to make that when A is positive, the shift is to the left, all right? And when it is negative, the shift is right, to the right. Okay? Explain why. I leave this for you to think about and respond to. Next slide. What happens when you multiply the function by -1? That's what I'm doing here. You can see I've got negative, 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 negative. Okay. Let's investigate. First, let's look at the quadratic. Okay, let me just bring this quadratic over. And here is y equals x squared, the red parabola. What if you stick a negative out front? What happens? You know? Turn it on. Voila. It pops up down below. It flipped it. Does this always work? Let's try the next one. I'll go ahead and paste that one in. Oops. Okay. And we flipped it, the quadratic. B is the radical. Let's bring over the radical. All right, there it is. Okay, there's my base function, square root of x. It's in red. Let's turn on the negative square root of x and point. There it is. Pops up down below. Okay. Did it flip it? I think it did. I think we can say it flipped it. Okay. Paste that one in. All right. Next was the exponential equation. Let's find that one. Bring it over. So again, my base function is y equals 2 to the x, and then I have y equals -2 to the x. Let's turn it on and see. Boom. Looks like ellipse, doesn't it? All right. Let's paste that in. And last but not least is the logarithmic equation. Let's see what happens to that one. That one's kind of a funky one, right? So here's the graph of log x, log base 2 of x, this red logarithmic equation again. And let's turn on the minus log base 2 of x, and we get that. Isn't that cool? Okay, so it flipped it again. Bring over my little graph and paste it in. All right, very good. So putting a negative sign in front of the x inside the function causes a reflection in the x-axis. All right, it's going to be a little bit hard to write that, but let's just see here if I can. Reflection in the x-axis. All right. Now, what about putting a negative sign in front of the x inside the function instead of outside? Because if you notice these here, I have the x's out front. What if I put the x inside? Let's just take a look at those. Bring over my first one. We have the parabola. All right, is it coming? Here it comes. And you can see I've graphed y equals x squared, and then I put the negative inside with the x. Let's turn it on. What's going to happen? Oh, look at that. It turns from red to blue. It's the same graph. Okay, nothing to show there. All right, what about the next one? Let's bring over the square root function. All right, coming. Whoops, I just dropped it. Right. Oh my, just had a little accident with my graph there. And now I lost it. There it is. Okay. So here is the square root, and inside the radical sign I put a negative x. Well, you know you can't take the square root of a negative number, so what's this going to do? It's going to error on me? Let's check it out. Turn it on. Oh yeah, look at that. Okay, it does exist. It flips it. All right, let's try the next one. So the quadratic didn't seem to, well, it seemed to turn red into blue, but here it moved the red across. Is that the same thing as what happened with the quadratic? Let's take a look at the next one. Let's do the exponential next. Try not to drop it this time on the way over. All right, there is my y equals 2 to the x. Then I have y equals 2 to the negative x. Let's turn it on. What's going to happen? Boom. Aha. All right. And last but not least, we have the logarithmic equation. Bring that little guy over. Okay. And you can see I've got, whoops, I got y equals log base 2 of x, the red curve here, with the asymptote as usual. And then I put the negative x inside, and when I turn it on, there we go. All right. So, move that away. Okay, so it seems like there's a difference here. One of these doesn't seem to change. Which one? Well, they all changed, but the first one didn't move the graph at all, and the others did. Okay, so something happened. So I leave you to answer the questions at the bottom. All right. So putting a negative sign in front of the x inside the function causes a, how would you call that? I'll leave that to you. All right. Next, let's see what happens when you put in a multiplier. Ooh, we are at 24 minutes. I meant to have a shorter video, but there's a lot in this video, I guess. So a multiplier, k. So it says here, putting in a multiplier k can stretch or compress the function. All right. Let's take a look what happens. Let's first do the quadratic here. Bring over the quadratic. Hopefully I can find it. All right, so there it is. And you can see here that I'm going to turn it off, but we have y equals kx squared. Then I put in the slider, and then I put on the green one is the base function. It's just y equals x squared. Now let's move the slider around. Oh, look at that. So when the slider is 0, then it should uh, cause there to be just a flat line because k is 0. But when k is 1, it matches, right? If k is bigger than 1, the red is inside the green. And if k is less than 1 but bigger than 0, it's outside the green. Okay? So it looks like it gets thinner or fatter, but notice the vertex is not changing. So it's not up or down and it's not sideways. We call this stretching or compressing. All right, I'm going to move this guy out of the way and paste my little picture in. So we have this one. And I'll paste that in here. Okay, and I left k on, I think I left k on 3. So the red is the thinner k equals 3, so it's 3x squared versus x squared. Okay, let's go to the next one, the radical equation. Bring that little guy over and so let me just drag this over. All right, so here we have y equals square root of x. So there's our standard radical, our base function. And then if I put in a k here and turn it on, what happens here? Let me set k to 0 first. Or actually, I'm going to put k to 1 so it doesn't affect the graph at all. All right, turn this on and nothing happens. Well, it darkened the graph actually. It went from light blue to dark blue, right? If I click on this. So now let's slide this over and you can see what it does. Moving up and moving down. So I think of this as like a rubber band that's getting pulled up or getting squished down. So that's why we call it a stretch and we call it a compression. Okay, I'm going to leave it on 3 here, I guess like the others. Take it up to 3. And we get that. Okay, let's paste that in to my little picture. Okay, next is the exponential. K is 2 to the minus x. Bring that one over. Oh, it looks like I used something else when I graphed it. All right, well, that's fine. I will show you. I used e to the x instead of 2 to the x. And I didn't use negative x either. So there's a little change there. Let me just mark that on here. So I am making this going to be, instead of that, I'm going to make it k dot e to the x. Okay. All right, where's my graph? Just disappeared on me. Oh boy. Drag this over. All right. So we have, oh, that's the logarithmic. I think I lost the graph. I dropped it. You drop things in this, you're not coming back. So I'll just go get my screenshot and I'll bring it up. So this one here is going to give me what I want. And paste that in over here. Okay, so we have, did we put in here? We have k e to the x. And of course, e to the x should go through the point 0, 1. So it's the green. And then I have 3 times e to the x. So it should go through 0, 3. And you can see that it does. That the red line goes through the y-intercept at 3. Okay. And the last one, k log base 2 of minus x. Oh, I don't think I graphed that one either. But I guess I changed my slides. But here is k log natural x. So I'm going to fix that up here in a second. But you can see again, the base curve is the green one, log natural of x, and it goes through 0, it goes through 1, 0, this spot here. Okay. And then when I multiply by 3, all right, we get the red curve, and it still goes to that same point, 1 comma 0. Check that out. And when I slide this around, no matter what I do, it goes to that point 1 comma 0. Isn't that interesting? Okay. And I'll leave the k on 3 because I think that's what I put in the attached graph, and we'll put that in there. So I'm going to make that y equals, since I changed it, I'll call that k ln of x, okay, instead of what's there. And lastly, I will put in this one and paste it in. All right, we have 2 more examples to do, and then we'll be finished. Trying to keep this not too lengthy. We've been through a lot. All right, example 6. You can have any combination of these vertical, horizontal, reflection, stretch transformations. So what are the transformations below? So here's the meat of the lesson. This is what I was trying to get to. How do you graph this? Well, obviously you can use Desmos, but I want to identify what transformations there are from the base function. All right, so we can see here, looking at this graph or this function, that we have a -3. So now hopefully we know that's a vertical shift. We have a -2, that's a horizontal. And the vertical is down 3, right? -3. And the horizontal, when it's negative, it's to the right. So it's +2. So we could graph our ln function, and then we could shift it over. So ln, as you know, goes through this point right here, 1, 0. It comes up with an asymptote, and then it curves away. Okay, somewhere around there, and it curves away like that. But if we pushed it down 3 and to the right 2, then it's going to look like, let's try and change this a little bit. Pushed it down 3. So this point's got to go 1, 2, 3 down here, and to the right 2. Boom, boom, here. So this point is going there. All right. So it goes like this then instead. Okay. And it's asymptotic. All right. And I can put in the asymptote. Let's do that. Let's stick it in with this. Do I have an asymptote way here to do this? Let's try this. It's going to be a little funny. We shifted the asymptote over to 2. Okay. And you can graph that and check that in Desmos. And the last one on this example is now we have a square root out front, which means a reflection in x. Reflection in x. We have vertical down 3, and we have horizontal left 2. All right. So we know the square root looks like this, goes to 0, 0, 1, 1, 4, 2, and so forth. And we're going to reflect it. So I'll push this in red. So we will go down here like that. That's first step. And then we can push it down 3. So 1, 2, 3 it goes down here. All right. That's not too good, but anyway, goes like that. So it goes from here to here. And then we're going to go horizontal to the left 2. So finally, it's going to go over here. I'm going to put it in green. It's my final answer. Goes left 2, and 1, down here, and on down this way. All right. So there's my final answer. I'm going to erase the other points. Don't need them. All right. This is gone. This is gone. This is gone. Again, you can put it in Desmos and check it. Okay. Last problem. Boy, we're at 34 minutes. I'm sorry. This is taking longer to explain than I thought. Okay, last problem here is this. Which of these functions have vertical asymptotes or horizontal asymptotes? Identify the asymptote. So hopefully, having done this Ed Puzzle video, you have seen examples of all of these, and now you know what they look like. So I know x squared, of course, is a parabola, and we know that has no asymptote, right? None. It has a vertex, it has a bottom, but it doesn't have an asymptote. The next one, 2 to the x minus 2, it certainly has an asymptote, a horizontal asymptote. And normally it's the x-axis, but this minus 2 pushes it down. So the asymptote would be -2. Okay? Well, I should write it as an equation. Y is -2. Let me just write that. All right? Y is -2. This one, e to the x, same as 2 to the x. It's another exponential curve. And this time the asymptote is pushed up. So the asymptote, y is 2. Log base 2 of x, well, you know that log, it looks like this. It comes up and then it curves over. They certainly have vertical asymptotes. So the asymptote is going to be x equals 0. Okay. And last, minus ln x. So you know this flips it over the x-axis. ln looks like this, just like log base 2, but this one gets flipped over. So it's going to this. Okay. And it has a vertical asymptote also, same as the other one. The asymptote hasn't changed, x equals 0. All right, so that's the background on how to interpret graphs and to figure them out by knowing what the base function looks like and what all these different parameters, these different values inside the function mean. Rock the practice, enjoy graphing, and remember, as Mr. Bean says, it's nice to be smart, but it's smart to be nice. Peace out.